Homework 14, Chapters 3.11, Problems 1 and 6. The first problem reads, a hollow circular tube having an inside diameter of 10 inches and a wall thickness of 1 inch is subjected to a torque. Determine the maximum shear stress in the tube using the approximate theory of thin-walled tubes and the exact torsional theory. Does the approximate theory give conservative or non-conservative results? So the equation for the approximate theory of thin-walled tubes is this one. So we have our torque, our diameter, and a thickness. So we have everything we need to solve for it, just keeping in mind that the radius that it's asking for is the radius of the centered line. So if we take our diameter and we add our thickness just one time, then that will give us the diameter to the center of the area, and then of course cutting that half gives us our radius. And we can calculate it and get our answer. Next, for the exact torsion theory, we have to use the equation we all know and love, TR over I polar. Gives us this whenever we plug in our polar, and keeping in mind that R is half of our diameter of the outside, then we can plug everything and get our answer. So 6.3 KSI is less than 6.8 KSI, which means if we were to believe that this was true using our approximate theory, then we would say it is non-conservative, because we could say, oh, something is going to give some stress. If we put some torque on it, this torque will only create 6.3 KSI of stress on our shear stress in our element. And when the true thing is that it actually will create 6.8 kips. So you are undershooting the true value. And the reason this is non-conservative is because we're saying, or we think that we have more leeway than we actually have, and that's dangerous. A thin-walled circular tube and a solid circular bar of the same material are subjected to torsion. The tube and bar have the same cross-sectional area and same length. What is the ratio of strain energy in the tube to the strain energy in the solid bar if the maximum shear stresses are the same in both cases? For the tube, use the approximate theory of thin-walled bars. So it's asking for a ratio, and recall that strain energy is some torque squared times L over 2G times polar inertia. The reason I have J here is because in this class, J denotes that we are getting an approximate polar inertia. And since it says to use the approximate theory for thin-walled bars for our strain sub 1, then that means we're going to be using our approximate polar inertia as well, which we denote as J. So, because they're the same material and the same length as stated in the problem statement, we can completely and already get rid of a ton of stuff. We have our L's are the same, our G's are the same, and then 2 is the same as 2. So we have this little ratio, which we can simplify as this. And due to using our shears from our two different types of equations, we have our exact and our approximate for our tube. We're going to be plugging those in, solving for our T1 and T2. So our median area is not the whole area, it is the area with respect to the radius that goes in the middle of the path. So when we solve for T1 and T2, this is what we get. And a approximate polar inertia equation is defined as such. So we're going to plug all of this into our equation, and this is where we're going to get. We're going to try to cancel things out. And I need a little bit more space, so let me clear all of that. This is the algebra behind it. I'm not going to go through every step. You can look at that yourself. But what we get here is this thing at the bottom left. Now notice it is in terms of R1 and R2, and that is not good enough because basically what it's saying here is that our strain depends on the size, which isn't true. So we want to get it with respect to areas, which is why I have these drawn out. Since R1 is our approximate theory, our area is this area. It's 2 pi RT, and this isn't the area inside of the circle. This is just the area of the cross section. So you might be used to doing your outer diameter minus your inner diameter, or both of them squared, of course, and then those are in parentheses, and then times pi over 4th. But that would be exact, since again, everything we're doing for strain sub 1 is using the approximate theory, so this is our area. And then our area for our tube, or not our tube, but our cylinder is just a generic area. So if I solve for R, I can plug that into our equation, do some more algebra, and get 4/2, or in other words, 2 as my ratio of my strain energy in my tube over my strain energy of the bar. So there's two things that we went over. Both of them are types of approximations. We have the approximation theory and torsional constant J, which is just an approximate polar inertia. So why approximation theory? Why do we approximate if, one, it's not guaranteed to be conservative? In other words, could give you false or misleading values in the incorrect direction. For example, if it had been conservative and it had said for our one problem where let's say it was 6.5 kips per square inch, I don't remember the exact value. Let's say our approximation had given us 7, then that would not be bad because you would not put too much torque on it because you're saying, oh, it's already past what our maximum is, and thus we should stop adding more torque, and that therefore is conservative. So why would we use an approximation theory if it's not even, like, we can't guarantee that it will be conservative, and we have equations for the exact value? Thank you for asking. Great questions. Let me explain. So in real world application, you might have some shape that you're working with, and there's just not some standard way of solving for it yet. And you, as the engineer, have to figure out, okay, but I still need this thing to function. So how can I approximate it, at least? Because you'll learn later in classes, you do a lot of approximation in engineering. Things start to become less and less exact, which is fine. And there are really good methods for approximating, but there are limitations to approximating. And the point of us covering this in class is to make sure you understand that ideally you want to have an exact answer, but sometimes you just can't do that. And so you will have to approximate. And so we have in the book equations that are used to approximate and get exact values for types of geometries that we do have exact values for, or that we can solve for quite simply enough for a sophomore level class in college. And you can see the pros and cons of each. Sometimes the approximation theory or approximations will be used just because the amount of work that will be necessary is dramatically less. And so that's advantageous depending on how much precision you need for something. And sometimes it just doesn't even matter. So that's what's going on. You don't have to use approximation theory on your tests itself. Maybe there'll be a conceptual question. However, we're going to be sticking with more of exact things. Anything with very few applications. Don't worry about that. That's not going to be on the test. And then, of course, the torsional constant is the approximation theory's version of polar inertia. And that's pretty much all you need to know about J. There's equations for J's for different things, and then again, in a future field, if you happen to be working on the things that we talked about in this class, you might need to know how to find a torsional constant, but we will not be covering that in this class. Hopefully this was helpful. I hope you enjoyed.